Hi, in this video, I want to go over sections 11.1 and 11.2 of Introductory Statistics in OpenStax. These two sections are the beginning of chi-square distribution. So in chapter 11, we talk about a chi-square distribution, which is another distribution like a z distribution or t distribution. We use a chi-square distribution for different reasons, for the test of independence, for the goodness of fit test, for the homogeneous. But in this class, we go over only the independence and the goodness of fit test. So chi-square distribution is also like a z and t distribution is a family of curves. But the only difference that the chi-square distribution has is that it's not a symmetric distribution. It's always positively skewed, or we can say that's a distribution which is skewed right. Okay, but if you remember, when we talk about the z table or z distribution or the t distribution, we said that they are a normal distribution. They are symmetric. But the chi-square distributions is not symmetric, and it depends on the degrees of freedom, like a t distribution. And as the degrees of freedom increase, the chi-square distribution will approach a normal distribution. And you can see that in the picture. If the degrees of freedom is 30, you will have a normal distribution instead of a skewed right distribution. So why do we use the chi-square test to test and see if the frequency distribution fits an expected distribution? Sometimes we have the result of a study from the past, and now we want to see if we have a sample, if we have a new sample, and we test over that new sample, does this sample, the new sample, or the new observed frequency fits the expected or the expected distribution or the result from the past studies? This is called the goodness of fit test. That's why we use the chi-square goodness of fit test, because we wanted to test how good the observed frequency fits the expected frequency, how good the result from the sample fits the theory or to the actuality. To write the null and alternative hypotheses in this hypothesis test, we always assume equality for the null hypothesis. So we have to say that the observed distribution fits an expected distribution in the null hypothesis. So in alternative, we say does not fit. The observed distribution does not fit the expected distribution. And in this hypothesis test, we can write the null and alternative hypothesis as a whole sentence of words as well. We don't have any notation for the goodness of fit test, like a mean or the standard deviation or the proportion. We have to write the null and alternative hypothesis by a full sentence. And you will see in the examples that how we can write that. And sometimes, instead of saying that the observed distribution fits the expected frequency distribution or the frequency, we can also say that the expected distribution, it's a uniform distribution, fit a uniform distribution. Or we can also claim the whole, write the whole claim on the null hypothesis as what we agree on for the expected distribution. The notation that we use for the chi-square goodness of fit test, since we have two types of frequency, observed and expected frequency. Observed frequency are the results or outcomes of that from the sample, which we show by O. Expected frequency are the results from the past study or what is in a claim, and we show by E. K represent the number of categories that we have, because we will have an observed and expected frequency for each category. N represent the total number of sample, and the P represent the probability for each sample data. Sometimes we don't have the expected frequency for each category, but we have the probability for each category. That based on the probability, we need to find the expected frequency. So like any other hypothesis test, we need to check the requirement. So to check the requirement, first of all, make sure that you have both of the observed and expected frequency. If in the problem, both of the observed and expected frequency is given to you, you can check the requirement and start the hypothesis test. But if you see you have the observed frequency but not the expected frequency, you need to find the expected frequency first and then check the requirement. So what are the requirements? To check the requirement, we need to make sure that the observed frequency or the result from sample data have been randomly selected. So the sample, the data have been randomly selected or completely random. And the second requirement says that each of the expected frequency must be at least 5. All the numbers that you see here as the expected frequency for each category must be at least 5. It means 5 or more. After checking the requirement, then we need to write the null and alternative hypothesis. So, as I said, the null and alternative hypothesis for this test may be written in a sentence. What we can say that the frequency counts, which means the observed frequency, agree with the claim distribution, which is the expected frequency. And we always set the equality for the null hypothesis. If it's agree, fits, it's on the null hypothesis. And if we say agree on the null hypothesis, or the alternative, we say do not agree. If we say that the observed frequency fits the expected frequency, for the alternative, we say the observed frequency do not fit the expected frequency. We can also say that the observed frequency fit a uniform distribution. And uniform distribution means all the expected frequency are the same. And after finding the null and alternative hypotheses, we need to find the test statistic. The test statistic is coming by this formula. This is a notation for the chi-square test. It's like an x, a fancy x, with the square on top of that. So we call this one the chi-square. And it's equal to the sum of the observed minus expected, and then s squared divided by the expected. So we have to do this, we have to find this result for each category, and then at the end, add all of the answers for each category. Then after finding the test statistic, like any other hypothesis, we have two different methods. We can use the p-value method. The p-value methods are usually, you can find the p-value by the technology, or you can use the rejection region method if you want to use, work on the problem manually and use the table. And if you want to use the rejection region method, you know that you need to find critical values first. And the critical values for the chi-square table depends on the degrees of freedom, which the degrees of freedom is always k minus 1. K means the number of categories minus 1. And you know that the goodness of fit test, because it's a chi-square test, is always a right tail test. That means after finding the critical value, we always use greater than sign, because all those numbers are the area to the right. Because the chi-square distribution is a skewed right distribution. Now let's see how we can find the expected frequency. So you always have the result from the observed frequency, because observed frequency means the result from the sample. It's always given to you in the problem. But how we can find the expected frequency? It depends if we have equal expected frequency for each categories or unequal expected frequency. If the expected frequency for all categories are equal, which it means the expected frequency fit a uniform distribution, which is follows a uniform distribution, or it mentioned that the expected frequencies are equally likely. So that means the number for the expected frequency for all categories are the same. And how we find that number? By just dividing the sample size by the number of categories. But if we have unequal expected frequency, and they are not the same, we need to find expected frequency for each of those categories. And how do we find that? Based on the probability for each category. In this case, the probability or the percentage of occurring must be given to you for each category. Then we multiply the probability, which is P, for each category by the sample size, which is N. This is how we find the expected frequency for all categories. If we have equal expected frequencies, all the expected frequencies are the same. We just find these numbers and put it for all of the categories. But if they don't have equal expected frequency, you need to use this formula for each category separately and find the expected frequency. Let's look at an example. For example, it says a single die is rolled 45 times with the following result. Assume that the die is fair and all outcomes are equally likely. That means the expected frequency for all categories are the same. So when you roll a die, the outcomes are 1, 2, 3, 4, 5, and 6. And after rolling the die 45 times, we see that 13 times it occurred 1, 6 times we had 2, 12 times we had 3, 9 times we had 4, 3 times we had 5, and 2 times we had 6. These are the observed frequency. Now how we should find the expected frequency. Since all outcomes are equally likely, that means the number for the expected frequency is the same for all categories. And how do we find it? We need to divide the sample size by the number of categories. Sample size is 45. How many categories do we have? 1, 2, 3, 4, 5, 6 is 6. And if we divide 45 by 6, we get 7.5. Which it means the expected frequency for all categories is 7.5. And it's the same for all categories. This is how we find the expected. Now it says, if we claim that the die is not fair, and the die is loaded so that the outcome of one occurs 50% of the time, and the other outcomes like 2, 3, 4, 5, 6 occur 10% of the time. So you see that the expected frequency are not the same for all categories. So we need to find the expected frequency for each category, and by multiplying the probability of that category by n, which is the sample size. Since we roll the die 45 times, we need to multiply 45 by the probabilities. How much is the probability of occurring one? 50%. And if I multiply 45 by 50%, I get 22.5. So the expected frequency for one is 22.5. And since all other outcomes is 10%, the probability, 10% means 0.1, and multiplied by the sample size of 45, it gives me 4.5. So the remaining categories expected frequency is 4.5. So remember, if the expected frequencies are not equally likely, you have to have the probability to find each of the expected frequencies. Okay, the first example. It says a tax preparation company randomly select 300 adults and ask them how they prepare the taxes. The results are shown. That's the result from the survey, this table. Find the observed frequency and the expected frequency for each tax preparation method. Okay, we know that the result from the survey, it's my observed frequency. All these numbers are the observed frequencies. How many categories do we have? 1, 2, 3, 4, 5 categories. And we have the observed frequency for each of the categories. Now, to find the expected frequency, we need to know if we have equal expected frequency or not equal. It never mentioned that we have equal expected frequency. It's just given to us a table which shows the distribution of tax preparation methods from past studies. In the past studies, we know that the 24% of people use accountant, 20% use by hand, 35% use computer software, 6% use friends or got help from friends or family, and 15% of them use tax preparation services. These are the results from the previous studies. And each of these percentage are the probability for each category. So if I want to find the expected frequency, I need to multiply each of these probabilities by the number of sample size. The sample size is 300. And if I multiply each of these percentage by 300, I will find the expected frequency. So we have 300 in a sample, and I know that 24% use a content, and if I multiply 300 by 0.24, I get 72 as the expected frequency. Now we have both of the observed and the expected frequency for the categories. Now in same question, it says a retail trade association claims that the tax preparation methods of adults are distributed as shown in the table below. That's a claim. And they claim that the tax preparation methods of adults are like this table, which tells us 24% use accountant, 20% by hand, 35% computer software. A tax preparation company randomly selects 300 adults and asks them how they prepare their taxes. And the results are shown in this table. That's a result from the sample, which is my observed frequency. If alpha is 1%, test associations claim. So when we have a result from a survey and a result from the previous study, and when we want to have a hypothesis test to test the associations claim, it means we want to see if the observed frequency fits the expected frequency. Do they agree with each other? So that's a goodness of fit test. Okay, anytime we want to see if the result from the sample fits the result from the claim distribution, fits the claim distribution or fits the result from the previous studies, we use goodness of fit test. And for a goodness of fit test, I need to have both of the observed and expected frequency first. Right now in this table, I have percentage. I need to find the expected frequency. And we did it in the previous slides. So now we have both of the observed and expected frequency. We can start a hypothesis test. These are the steps that we need to follow for a hypothesis test. First, we need to check the requirement. We need to make sure that the observed frequencies from a random sample, and the expected frequencies are at least 5. We need to write the null and alternative hypothesis. We need to know the alpha, and since we want to use rejection region method, I need to know the degrees of freedom and use chi-square table to find the critical values and the rejection region. Then I use the formula to find the test statistic, and based on the result, if it's in the rejection region or it's not, I will make my decision and interpret the decision. So let's follow all these steps. We have the numbers for the observed and expected frequency. Let's check the requirement. First, are all observed frequencies random? If you go back to the question, you see that it says randomly select 300 adults. That means, yes, they come from a random sample. Second requirement, are all expected frequencies 5 or more? And if you look at these numbers, you will see, yes, they are at least 5. They are 5 or more. So that means this problem satisfies all the requirements, and we can use the chi-square goodness of fit test for this distribution. After checking the requirement, I need to write the null and alternative hypothesis. Since writing a null and alternative hypothesis depends on the claim, and the claim says that the tax preparation methods are distributed as, based on this table, you can write all the information from the table as your null hypothesis, or you can say that the observed frequency fits the expected frequency. Both of them works. It doesn't matter which one you use. You can write everything from that table in the null hypothesis, and you say, okay, the expected distribution of tax preparation method is 24% by accountant, 20% by hand, 35% by computer software, 6% by friend or family, and 15% by tax preparation service. And we know that's a claim. Or you can say that the distribution of tax preparation methods is the same as the expected distribution. And for the alternative, we say they are different. So the distribution of tax preparation method differs from the expected distribution. After writing the null and alternative hypotheses, now it's time to find the critical values and the rejection rate. To find the critical value, since we are using the chi-square table, which I will show you right now, you need degrees of freedom and you need to know what's alpha. The degrees of freedom is k minus 1. That means the number of categories minus 1. How many categories do we have? 1, 2, 3, 4, 5. We have 5 categories, and 5 minus 1 is 4. So the degrees of freedom is 4, and alpha is 1% because the problem is given to us. Now I look at the chi-square distribution, which is this table. So the degrees of freedom is 4, alpha is 1%, and we end up to this answer. This is the critical value. So my critical value is 13.277. And since the chi-square distribution is always a right tail test, you always assume that the rejection region is the right tail. It means any number that's greater than 13.277. Okay, because when you have this number, that's your chi-square, the critical value, you always have a right tail test, and that's a rejection region. Just greater than that. That's always, I say always. Okay, so remember that after finding the critical value, you always say the rejection region is greater than that number. Then we need to use the formula to find the test statistic, because we want to check if the test statistic falls in the rejection region or not. So if you remember the formula, in the formula, we need to subtract each of the expected frequency from the observed and then square it and then divide it by the expected frequency. These are the observed, these are the expected. So in the first category, what we have 60 minus 72, and then we need to square it. Then divided by the expected frequency, which is 72. For second category, we have 43 minus 60. We need to square it and then divide it by the expected frequency, which is 60. For the third category, we have 117 minus 105. Then we need to square and then divide it by 105 because that's the expected frequency for that category. For the next one, we have 29 minus 18. Square it divided by 18, which is the expected frequency. And the last category, 51 minus 45, square it divided by 45, which is the expected frequency for that category. And after adding all these results, we get 15.71. After finding the test statistic, now it's time to check if this number is in the rejection region or not. The rejection region tells me any number that's greater than 13.2 must be rejected. And this number is greater than 13.2. Yes. So what do? We have to reject the null. So it's in the rejection region. We need to reject the null. And you know that the null is the claim. That means you need to reject the claim. So what do we say? We say there is enough evidence at 1% level of significance to reject the claim that the distribution of tax preparation methods and the association's expected distributions are the same. We need to reject this claim. It means they might not be the same. Okay. Now we are done with this example. Let's look at another example. It says a researcher claims that the number of different colored candies in bags of dark chocolate M&Ms is uniformly distributed. That's the claim. To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms, and the results are in this table. Then you know that the result from the sample is always my observed frequency. And how many categories do we have? 1, 2, 3, 4, 5, 6 categories. Using alpha 10%, perform a chi-square goodness of fit test to test the claim or the expected distribution. It's a typo here. And what can you conclude? Okay, for starting a goodness of fit test, we need to have both of the observed and the expected frequency. I have the observed frequency, but I need to find the expected frequency first. How do we find the expected frequency? Let's look at the claim. The claim says that the number of colored candies is uniformly distributed. Uniformly distributed means the expected frequency is equally likely. That means the expected frequency for all categories should be the same number. How do we find that number? By dividing n by k. N is the sample size. K means number of categories. And if you divide 500 by 6, you get 83.33. And that's the expected number, which is for all categories. That's the expected frequency for all categories. Now I'm ready to start a hypothesis test because I have both of the observed and expected frequency. I know. To start a hypothesis test, I need both to check the requirement. I need to check if the observed frequency coming from a random sample, and I need to check if all the expected frequencies are at least five or more. And you see that this question satisfies both of the requirements. Okay, now let's start the hypothesis test. Write the null and alternative hypothesis. To write the null and alternative hypothesis, you need to know the claim. You can write the claim, the uniformly distributed in the null hypothesis. And alternative, we say it's not uniformly distributed. So for the null hypothesis, we can say the expected distribution of different colored candies in bags of dark chocolate M&Ms is uniform. So for the alternative, we say it's not uniform. And remember that the claim is on the null hypothesis. Okay, next step. We need to know the alpha. Okay, the alpha is in the question says that the alpha is 10%. And we need to have the degrees of freedom, which is 6 minus 1 because we have 6 categories, and 6 minus 1 is 5. And after having degrees of freedom and alpha, which is 10%, we need to look at the chi-square table to find the critical value. If alpha is 10% and the degrees of freedom is 5, so we get this number. That's my critical value. And since the chi-square distribution is always a right tail test, is a skewed right distribution, the rejection region means any number that is greater than 9.236. Now I need to use the formula and subtract each of the expected frequencies from the observed frequencies and then square them and then divide them by the expected frequency, which is the same for all categories in this example, and then add them together. So you can do all these steps in a table like this, or you can do it like the previous example, just in math form. Okay, now we end up with a 3.01 as a chi-square test. After finding this, we need to check if it's in the rejection region or not. The rejection region says that must be greater than 9.2. Is this number greater than 9.2? No. So it's not in the rejection region. If it's not in the rejection region, that means I fail to reject the null. If I fail to reject the null, since the null is the claim, I can say that there is not enough evidence at 10% level of significance to reject the claim. This time we do not have enough evidence to reject the claim. That the distribution of the different colored candies in bags of dark chocolate M&Ms is uniform. So you know that you always, after rejecting or failing to reject, you need to just write the whole claim. So we say there is not enough evidence at 10% level of significance to reject the claim. That just mention the whole claim. Okay. Let's look at another example, and I will show you how you can use online calculator as well at the end of this example. Everything that we learned so far is just working on the problem manually using the formulas. I will work manually on this problem as well, and I'll also show you the online calculator that helps you find answer faster. It says employers wants to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences, and the results were distributed as in table. For the population of employees, do the days for the highest number of absences occur with equal frequency during a 5-day work week? Do we have equal frequencies for the expected frequency? Is the expected frequency uniform? Are they equally likely? That's a question. That's a claim. We want to test at a 5% significant level. And in the table, you have the number of absences in each day of the week. 15 absences on Monday, 12 absences on Tuesday, 9 for Wednesday, 9 for Thursday, and 15 for Friday. And you know all the numbers from the sample are your observed frequency. So I need to find the expected frequency first before starting the hypothesis test. When it says that the absents are equally during the week, that means we have equal expected frequencies. Since we have equal expected frequency, I only need to divide n by k to find the expected frequency. N is the number of samples, which is 60, and then divided by k, which is the number of categories, 1, 2, 3, 4, 5. And if I divide 60 by 5, I will get 12 for the expected frequency. It means that the expected frequency for all categories is 12. And after finding the observed and expected frequency, now it's time to find critical values. Since you want to use chi-square table, to find the critical value, you need to know the degrees of freedom. Degrees of freedom is 1 k minus 1, the number of categories minus 1. We have 1, 2, 3, 4, 5 days of the week, which is 5 minus 1 is 4. Alpha is, oh yeah, we forgot to check the requirement. Don't forget that to check the requirement, we need to make sure that all the observed frequencies are random and the expected frequency are at least 5, which they are. To write a null and alternative hypothesis, again, we can say that the absent days occur with equal frequencies, which is our claim. If you look at the problem here, it says, do the days for highest number of absences occur with equal frequency, which means the absent days occur with equal frequency. And we always put equal sign for the null, not equals, it's on the alternative. Or you can use this sentence instead of the first sentence. You can say the absent days fit a uniform distribution. If you use this one, you need to use this one for the alternative. The absent days do not fit a uniform distribution. Just use one of these options. The first sentence for each or the second sentence for each. And then degrees of freedom is k minus 1, which is, we have 5 categories, 5 minus 1 is 4, and alpha is 10%. Then we look at the, alpha is 5%. Then we look at the chi-square test table. Alpha is 5%. Degrees of freedom is 4. And the answer is 9.488. So the critical value is 9.488. And the rejection region is any number that's greater than 9.488. Then we need to subtract the numbers, the observed from the expected frequency from the observed, and then S squared, divide each of them by the expected frequency. And we end up to number 3. So the result from the test statistic is 3. But the rejection region tells me if it's more than 9, must be rejected. This number is not more than 1. And it means it's not in the rejection region. If it's not in the rejection region, you fail to reject a null. If you fail to reject a null, that means you fail to reject a claim. That means that there is not enough evidence at 5% level of significance to reject the claim that the absent days occur with equal frequencies. So we can't reject it. We may be able to support, but we don't know. The only thing that we know that we cannot reject the claim. Now let's see how we can use online calculator. Okay. If you open online calculators and you go down to number 21, that's a goodness of fit. And if you open this test, the goodness of fit, you will see that it asks you to type in all the observed frequencies and the expected frequency, and then it will calculate it for you. Okay. So to make this faster, I already typed the number for you. I already typed all the observed frequencies and the expected frequencies, which they are all equal, and they are 12. So make sure that do not put any space, between the numbers and the commas. Now I will calculate, and you see that the chi-square from the online calculator is the test statistic is again 3, and we got 3 as well. If you need a p-value for the question, make sure to use calculator, TI-83 or 84 calculator, or the online calculator. And the p-value is 0.55. If you want to make your decision based on the p-value, remember that the p-value must be less than or equal to alpha if you want to reject the claim. Alpha is 0.05. So if alpha is 0.05 and the p-value is 0.55, is p less than or equal to alpha? No. We know that the p greater than alpha. If you p greater than alpha, you fail to reject the null. Fail to reject. And you know that with the rejection region method, we also made this decision and we failed to reject the null. So we can say at 5% level of significance, there is not enough evidence to reject the